everyone. Let's get back to work. Welcome to EE360. A quick video I wanted to do for y'all because it didn't show up today. But howdy y'all, how we doing today? So this is usually how I kind of did my videos back in the day. Yeah, that Friday video we did was kind of low-key, not as best as I thought. But I'm going to try and hopefully help you guys with finishing the assignment and maybe going over some advanced MATLAB tricks I want to show you, because I can feel like some of the students, like I'm getting this vibe. Like some of the students, I think they're thinking this is boring, which is good. If it's boring, that means you're following along. I don't really have to help you as much. But I'm trying to hit those students who are probably still scared, who are still shaking, maybe sweating about, oh gosh, I don't know if I can finish this assignment in time. Don't worry, my job is to make sure that everyone can successfully finish these assignments, feel good, get an A, and go celebrate and be like, yes, I can study for that exam now. So let's get to it. So if I were to show you some advanced MATLAB tricks, what's the first thing you should be doing? Well, the first thing you should be doing is actively going to, let's pull this puppy out, my little CMOS CDU page that I have right here. Let me see if I'm recording. Yes, I'm recording. Alright, so for those who don't know, I do have an example from Friday's lecture that you can download right here. Just click on it. I'll walk you through it and just pull that down. If I were to pull this down, here it is, my new little zip file. Extract all. This is what you would all be doing, by the way. That's if you wanted to. Get this folder right there. Double click on it, and you can see it's. Oh, ignore that too. Here's our little dump file. Open it. Double click it. I have it opened in a different file. Let me pull this guy out. And if you were to do everything correctly, let's see. I have the work that we've done from Friday. Hooray! So if you wanted to run this, let's go to CLC. Actually, let's run section. As you can see, it says Control Enter. You can run the example we were doing on. Oh, there you go. The little quiz that I gave everyone. Hopefully that was really helpful. And by the way, thanks for those who are emailing me their quizzes. The reason why I was also doing that too was I also need some type of participation since it's a discussion and they're asking me to figure out how to like get people to discuss. I guess the best way is the quiz. And plus, Dr. Stever hasn't given me a attendance sheet or a grade book, so I'm trying to create a grade book based on the last names you've all provided me. So some of you guys have like 2 last names, so it's good for me to figure out, okay, what names should I be recording, what shouldn't I not be recording. So thank you very much. You guys are all putting in your work to help me make my life a little more easier, so then I can produce more content for you guys. So if I were a student shaking in class, I'd probably be like, David, what do I do? Help me with the assignment. And no worries, I got that assignment for you. So I assume everyone has already read up to, well, this first page. You can see how to generate matrices. If you type this into MATLAB, get this nice square. Oh yes, there's some functions in here too. So the one thing I'm going to be looking at in these assignments is, are you using the functions that are defined in this assignment? If you guys are using anything else, I'm taking points off. Like there's a special function, there's circ shift. Don't use that. I know some of you guys are probably looking at some old code somewhere. No, we're here to try to figure out what's going on. We're trying to figure out, okay, can I do this assignment with what I'm given, the bare minimum? And I want to make sure even top students, the bottom students, they're all at the same advantage, unless you want to make your papers pretty. But let's see. Everyone in this class should be able to do this. Exercise 1. And I did have a typo here. I'll have to change this. I don't know why I was thinking this. I was thinking R and this. Oh yeah, to generate that, if anyone wanted to know. I didn't do that in class, but let me show you. Exercise, what's it called? 1C. There we go. 1C. A ramp. So if you were to do this, generating a ramp function, we're going to give our same time, which is, well, we can define it as that if you wanted to. Oh. And yeah, let's just do it from -10 to 10. It's not the assignment, but you guys can change that if you want. Let's see. Actually, let me click on that. And let's see. Well, if we were doing this, if you notice the pattern, just literally type in R is equal to N. Oh, N figure, I don't know, 10, let's call it 10. Stem N R, where this first column is our x-axis, what's our time. This one is our y-axis, which is, well, our data. And then if you want it to be more formal, you can do this R. Let's make a red line. Okay, blue if you wanted to. Filled. Actually, I'll show you what happens if you don't put that there. And line width. And 3 because I like big, thick numbers. Title. The ramp function. Now I'm about to show you one advanced MATLAB trick, and you can see that right here. So let me try to see if I can remember. If you were to do an advanced title, so if you were to draw a figure, the things I'm expecting from everyone in this assignment is, first you got to have some X label. So you can put in whatever you want, and right? Then everyone will have to give me a Y label, which can be, I don't know, Y. And then a title. Wait, title. So there's a way of writing title, and I'll show you how I do it to make my assignments more prettier. So there's a thing called a subtitle, where if you draw like this, the ramp function, then you close that, and then you put this comma there, and then right here is where I can do R of N is equal to N, and then close that. There we go. So if you type the syntax, I'll show you what that does. So we're gonna put this little curly bracket, and then we're gonna put let me see, actually, oh, I made an error. It should be one curly bracket. So this goes, let me use a different color. This curly bracket here is gonna cover from here, ignore that, to ignore that there. That's really messy. Okay, if I were to blanket this again, point is, this needs to be one statement. So the curly bracket right here would need to cover this whole thing. I'll type it out, maybe it'll click in your brains. There we go. And then let's type in R, N is equal to N. And then close that. And now look, you see how this highlights that? If you click right here, I don't know if you can see another little underscore pop out. That tells you have a complete statement. Like, oh, this one too. See, you can see. I don't know if you can see that, but yeah, it should be fine. But let me show you what that runs. X label, N, Y label, let's run that. And look at that. Looks pretty cool, huh? And there you go. So you can see we have a big title right here, and you have the little title right there. This is how you create subtitles in MATLAB. And if you don't believe me, well, you could do... okay, I'll show you. Like, oh, what if you don't do that? Ramp function. You can type that as one statement. Now you get it all in one line. You see how it's all in one line? Right there. Yeah, it's in the way. Oh, it's okay. But that's how you would make more cleaner code. There you go. See? Now let me show you one more cool trick. So there's a way to get the interpreter window out. So if you wanted to type in LaTeX, which is a nice editor to have, interpreter, LaTeX, whatever people want to call it. So if you were to enter that, then it turns LaTeX mode on, which is a pretty nice function to have. And because we've created this from a previous session, this function that I have right here for y'all, enter, and look at that, you guys have some really nice code. And if you wanted to know what I was trying to do, let me show you how the LaTeX function works. If I were to copy this, remember that Dirac delta, Kronecker delta we were talking about right here? Let me type that right here. So remember this plot. Oh, not that one. Oh, let's see. The Dirac delta, or Kronecker. So we want this curly D, and I'll show you how to do it. Let me just make this red. Ah, that's annoying. Let me just... There we go. So you see how in our assignments we have this little curly D, this delta right there. I'm going to show you how to generate that right now so you can have really, really nice papers. So the function for that is if you type in this money sign, you can get this interpreter to work. So put this money sign, / delta. And then if you close that off with another money sign at the end, let's see what it does. Ah, you see that? I don't know if you can zoom in. Just make this font bigger, 14. There we go. No, not that one. There we go. Wait, no, Kronecker. See that right there? Now you can see that curly delta. And now you have something you can present. Actually, why do I have that? Kronecker delta. There we go. That looks better. There you go. So now you can have some nice titles, fancy titles. If you want to get even crazier, let me show you something cooler. Suppose you wanted to... should I show you? Okay. Font name. Let's suppose you memorize some of the libraries. Comic Sans MS. Let's look at what this does. Figure 2. Oh, that's not even a unit step. Let me just... that's gonna annoy me so much. Okay, because I'm getting my OCPD running on me. Okay. There we go. As you can see, you could also do the interpreter in your labels. I was trying to do something cool, but it's okay. But I was going to show you with this one. I think you can do it with this one. Time interval n. Font name. Comic Sans MS. Or Sans, however you like to say it. And there you go. Now you have Comic Sans that you can start annoying people with, or maybe get your hopes up for. So that's how you would make your titles look more pretty. Your labels, all your labels look really nice. Let's see what else I can show you. So double titles are nice. Interpreters are nice. You can also put interpreters in your labels, and you can change the font names. So that's what I wanted to show you. And now you're probably asking, all right, David, let's see. You can all generate that. All right, so someone's probably going to ask, okay, David, I remember you said something about the semicolons. When shouldn't I not use it? Or so for this example, let's look at this. If I were to do this, okay, exercise 3B. Or not 3B, 2B. There we go. Where you're trying to extract some stuff. So for our example, let's just do from -10 to 10, which means if I were to run this ramp function, so we have 0.1, 2, and 3. So if you were to visualize and you have your plot, what's our third point going to be? It's going to be this point right here, which has x is equal to 8, or the y value is -8. So that's what we would expect if we were to type in r of 3. So if you don't believe me, let's type it down here, r of 3, which is 8. Now you're trying to figure out, how do I make this presentable? So you can either do the following, where you can do a comment out third point in r of n is r of 3, and that would pop out whatever this guy's name is. Actually, let me just CLC run in section, and it would just give you the answer, but we can make it better. So there's a function called display disp, or actually I like fprintf, and we can do this. The third sample in r of n is, and then actually wait, %d, and then we can just do this. So this function, this printf, is one of my favorite functions. It basically, you can print out a statement. This will print into the command window, and then this %d basically says, oh, we're expecting a decimal or some number, which is this. So let me run that for you, and there you go. Oh, and also you have to start putting in new lines, which can be described as this \n, which gives you a new line, or you can do double new line. See, now you can have some really presentable code. And then, oh, if you wanted to copy paste this in u of n, let's put out the unit step. There we go. And there you go. Actually, let's go verify that unit step. Right here. Exercise, was that 1B? Unit step. Oh, that's because I'm using the different ends. -10. Oh. Let's run this. Run in advance. Run in advance. Run in advance. Okay, actually, let me go back to that unit step. Here's our unit step. Oh, I gotta change that title, where you can see 1, 2, 3. What's our third point? 0. There you go. Boom. Easy. Done. And you can see if we run this, third sample in R of n is 8, which is correct. And then our unit step, which is unit step. I wonder why it's printing like that. There we go. Actually, let me show you how to move that window if that is annoying. So let me remember. Calculating. No, I don't remember that code. I'll show you one day. But actually, for now, generating these windows like this should work. Alright, now the next thing we gotta go over. So now everyone can do 2. Should be easy. Number 3. So let's try to do this one, because someone's probably going to be asking, hey, how do I deal with this negative? So if you remember from studying from Dr. Stewart's notes, how to reverse something, you just put a negative in the time. So one of you guys are probably going to be like, okay, I'm just going to do some advanced math and type. No, don't do that. You already have a solution. You can use one of these functions. Flip up and flip left, right. So if I were to show you this exercise, exercise 3, A, 3A, which is u c of n, u of minus n. So you already know your unit step. So if I were to do C, let's do flip left to right of unit step LOL, because that's what I've defined right here. It can be anything you want. And now figure 11, I'm just going to guess, stem N, C, and then title. Let's do this cool thing. Exercise 3A, and then comma, C of n is equal to u of minus n. There we go. And because I'm OCPD interpreter, no text, and then x label n, and then y label c of n. There you go. And you can see it flips. See, that's the easiest way of implementing that function. So, and if you wanted to, let's run that puppy. And that puppy. There you go. That's the unit step. And now we flipped it. And you can see we flip on this 0 axis. Pretty cool, huh? All right. And let me show you this. So what if you don't put filled? So if you were to just do this, green, 4. It actually does fill it. I don't want to show you that. There we go. I don't know if you could see that, but those aren't filled. But if you were to fill it, just put a 1. Actually, let me change the color. red. See, it's not filled. If you put it filled, there you go. Now they're filled. So that's what I was trying to do with this filled command. It fills the holes. This line R just puts a line. I don't think so you need to put the line. I think you can get away with that. Oh, yes, you can. Because the reason why I put the line is because there's also a function called plot. But that's for analog signals. We're not going to deal with that until, I think, a couple weeks. I think your third assignment. I know your fifth assignment we will do a lot of plotting. So, but for now, just use stem. That's the only function you should be using to plot these. All right. So now we're getting a lot of progress done for today, y'all. And now let me see. You can easily do this. This is fun. This right here is literally your elemental multiplication. If you draw it on a piece of paper, if you draw this x of n, this one, if you were to multiply this by 2, what does it look like? Okay, all right. And then you have this Dirac delta. So, okay, I got to get to that point. So there's a property I need to show you. I don't know if Dr. Stuber's gone over it in class, but it's called the sifting property. So there's a property, and I think it's in his book. It's at the end. I'm going to show you. If you were to go to sifting property of the input pulse sequence, which is theorem 1.16. Just locate it on page 88. And yes, you got to study this whole book. Let's see. 88. So if you read this right here, this theorem, sifting property is basically whatever the Dirac delta says is whatever the entire function also has to say. So here's a great example. So if you have the Dirac delta x of, okay, if you multiply x of n times this Dirac delta, what's your result? So you know that the Dirac delta will say its name at n is equal to 0. And it will just kill the signal everywhere else. Which means the only number that will exist or come out of this little delta is when n is equal to 0. So whatever is at x is equal to 0. So this right here is one of the most important things you got to get out of this class. It's going to be on the exam, which is going to be in, I think, a week from now. So don't forget this. Another example would be, what if you had another signal, which is y of n and Dirac delta, the Kronecker delta of n minus 1. What's its name? So when does this become 1? At n is equal to 1, which means whatever this is at 1 will remain. Or y of 1. And that's it. So if you wanted to see this, actually, if you were to plot this at n is equal to 1, then whatever y of 1 is, of 1, that's the name it will say, and then everything else will be 0. You know what I mean, right? Just one point comes out. That's the sifting property. Just sift one value and that's it. So don't forget that. That's going to be an exam. We'll probably go over that more on Friday on a little quiz I'll create for y'all to make sure that you guys are well aware of what's going on. So let me talk to you about that. So if you were to look at this assignment, this right here is literally the sifting property. Just multiply this x of n times this. The only thing that will pop out is whatever is at is x equal to 0, which is, if you were to look at this, minus 5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5, which means predicting this will pop out times 2, and that means you'll probably have a graph which is going to look like Okay. I'm not lazy. Okay. 2. If you were to do 2 of x of n dn, all you'll get is whatever is at here, and then everything else is 0. And I think we just predicted it to be 2. And that is your answer for that part. So everyone should be able to do that. All right. Now the next part I want to get to everyone is exercise 4. So I did read this, and now I remember why. I remembered I wanted people to do estimated hand calcs because people were telling me, David, something's wrong. I don't know if this is right. I'm like, did you not verify it with your hand calcs? Like, no, I didn't even want to. I'm like, no, come on, man. So I make sure I want people to try to draw them, not like just precision, just do you know what it's going to look like? So you know what this is going to look like. This too. So here's another one. I think this is the one everyone was confused about. But if I were to do it, actually, let me show you one thing. And I highly recommend, if you need more practice, you can. Go. Oh. There's a lot of examples in the book. So if you wanted to, oh, he does have a signal right here. How to generate the signal cosine pi of n to 3, which is on page 23. Yep. Let's go to page 23. There we go. You guys are memorizing these definitions, eh? There we go. Oh. 23. There we go. So here's the code that you have right here. So that's how you would do it. There's 2 ways of doing it. You can either do this for loop, which is kind of painful, or you could just do it the way we were doing it, which is n is equal to minus 5 to 5, and then just punch in your n. I'll show you how to do that right now. So, doing the assignment. Oh, exercise 4 E. For E and F. So if I were to do CLC, clear vars, now we have a clear MATLAB we can work with, minus 10 to 10. You better be changing these numbers, by the way. And then E is equal to cosine of, what's our homework say? Pi n divided by 5. Pi times n divided by 5. If you were to hand calculate this, well, what's n is equal to, when n is equal to 0, what you're going to get? This is going to be all 0, which means you should have a 1 at n is equal to 0. And then if you were to go through the numbers, you can see that it's periodic by 5. Figure 20. Because I'm lazy. Well, we're trying to not waste time. Exercise 4 E. E is equal to, all right, now this is where you can get crazy. Cosine of backslash pi to give you the pi symbol. How do I do this? Okay, let me show you this. Frac to give you the fraction symbol. Pi n and then 5. Then let's put another money sign. There we go, money sign. Then E. Oh, that's because that's gotta be E. Oh, it doesn't like that. Frac pi 5. There you go. Wait, it didn't print out that one. Hit. There you go. Oh, you can't see that, but we could pretty graph it. Boom, you see that? Looks really clean, and now you can have some MATLAB to present to me or whoever you wanted to. So I'm trying to show you this to help you guys know what's going on. Now we could do the same thing with F. But that period is different, which is 11. Right? 11 times pi, because we could just copy this. 21 F. Then we could just put an 11 right here. F. Let's call this blue. There we go. And now you're probably, this is why I was asking you all to do your hand calcs, because you're saying, David, did I do something wrong? They look the same, and they should be the same. And this is a problem. It's a classical problem. You'll see it in EE360, which is considered you're undersampling. It's aliasing. So basically, with 11 pi, it's a higher frequency. But because our sampler is, well, this is the slowest frequency it could sample. This is also the same speed. It should be faster, but it's too fast. But our sampler is just okay. Not trying to make anything confusing, but point is, these plots should be the same because, well, our plotter is just, yeah, it's just slow. We're just aliasing. They should be faster, but don't worry too much about that. But that's what I wanted to get to, everyone. Like, you're probably going to ask, why are they the same? They should be different, right? That's your OCPD kicking in. Don't worry. So, that was a trick one I put on there. So make sure you guys are thinking. And then that one, you can generate on your own. You can use the absolute function. You know what that looks like. So that's why I say, draw your estimated hand calcs, just in case you don't know what's going on. Okay. This should be easy. Now, this is the one I'm going to try and tell everyone to type in their pieces of paper, type it in as optional. This is another classical case where you don't know the technique yet. You can do it if you want, but if you're trying to generate this signal from the information you're given, you're not going to have enough information because this is just upsampling. So basically, you need more points, but you don't have enough points. So how do I explain this? Well, you could do this. Actually, let me show you how to do that one. If anyone was curious about that. Exercise 5B. So first off, you need to generate that x, which is considered 5 divided by 6 dot power to the n. N is defined as minus 10. Creating my own numbers here. And then let's create a signal D. So from creating a signal D, you can't really create something from X because, well, you can't do that. Like if you were to try to do X of 2 times N, this is not going to work. Well, what is N? Actually, let me just run this. I don't know what it's going to do. Oh, there's another cool function called F9. You can just run a signal thing. Actually, let's run this. Yep, you see, because N is a negative number. Oh, N is a negative number. All this must be positive, so it's not going to work like, if you were to type this way. So for D, if you wanted to do this the correct way, instead of calling X, you just call whatever its name is. So the following. And then you just replace this with 2, parentheses 2 times n. There you go. Then figure 22. Let's call this one X. And magenta, I guess. 5. D something. Actually, let's call it 4C. 4C, which is X of n, which is equal to 5 divided by 6n. Alright, let me show you how to do that. Parentheses, 5, frac, 5, 6, that finishes that, parentheses, to the n. There we go. See how nice that looks right there? That's how you type in LaTeX. If you want any more help with LaTeX, just look it up on Google. It's easy. There's a lot of LaTeX things you can do. And then let me just copy this. 23. Let's call this one D. Let's call this one K. Oh, that should be C. And then that one should be 4B. 4B. 5B. Go. And this is called D. And then to do this, I'm gonna put this function. Here we go. And there you go. That's how you would do 5B. So the problem with this is, here's the original exercise. You're going from -10 to 10. However, for this one, you need more data. So that most data you have is this point at 10, but you need a point at 20. So actually, let me click on this one. So you see this point right here at 10? That's the most data you can have. So this purple data only exists from here down to here. Let me just click that right there. So from here to here is this magenta data, is what I meant to say. But you don't have these points up here, which is what makes this problem a little confusing, because you're trying to expect, oh, whatever signal I'm working with, but you can't do that. So that's why I'm asking people to leave this as optional. We'll type it in as optional, but now you know how to do it. But the only way to do it is this little loophole, which is to just call its name again. And then that same thing can go with this problem too, so don't worry so hard about that one. This one's another interesting one, and let me show you how to do 5C. So if you were to go into your notes, and this is where the people are going to start using search shift. Don't use it. I will take off points. Because he does it in the book. Don't worry so hard. Let me show you. It says code to shift the signal. So if you were to go to page 31. Oh, dropped my piece of paper. 31. How to shift a signal. And here you go. Let me show you. Page 31. And that's it. You just literally just change the time. You can either do this way or you can do it this way. I think I like this way. So here's the time of X, which is from 0 to 5. Draw your signal. And then all you do for the new signal is just add by 2. So let me show you. So if you were to do this unit step, remember a unit step? Exercise 5C. I'm going to create a new unit step. N, actually U is equal to 1 1 abs of n. Okay, so someone's probably going crazy saying, what the hell, David? So what I'm trying to do is, I know that if I were to have a time from -10 to 10, where the middle point is 0, so that means this middle point at 0, okay, if I were to do this, oh man, I think I'm making everyone confused with this one. Alright, I gotta show people how to do this because I feel like one of you guys are going so confused saying, David, what the hell? So let me show you step by step why I'm typing this. So start with -3. N is equal to -3 to 3, right? You got that. Simple. So if I were to do this, -3, -2, -1, 0, 1, 2, 3. That's what it's going to look like in MATLAB, okay? What's the definition of the unit step? The unit step is 1 is equal to 1 at n is equal to 0, right? And then everything past that is also equal to 1. Okay? And then you know else everything behind it is 0. Okay? This is the unit step. Okay? So what I'm trying to do is, you see a pattern. Okay. Let's look at the pattern. See, there's a 3 here. 1, 2, 3. 3 zeros. Okay? Here's a 3. 1, 2, 3. 3 ones. 3 ones. 3 zeros. Therefore, I'm like, oh, okay. So it depends on what number I have here, determines how many zeros I have. And then with the number here just determines ones. So if I wanted to do a function u, we can just create zeros, one row of whatever this first number is, which is n of 1. However, this needs to be positive, so put an abs to this, absolute value to that. So now you get however many zeros, that's it. Then put a 1, because that's our placeholder for this middle point. And then ones, 1 and end. So we're looking at the first point of n and the last point of n. So that's how you would code it. Does that make any sense? Yes? No? Maybe? Don't worry. Like, this is fundamental. If you're not getting this, please let me know. Like, the whole rest of the semester is based on these signals. So if there's any questions or any doubt, please let me know, because I want to make sure everyone is getting this. Like, if this is boring for you, thank you. That means I'm trying to do my job, or you're doing really great. But for those who are still scared of MATLAB, please let me know. Let's see. Oh, abs n 1. Okay, this closes that. That closes that. This. Oof, I probably have some typo in there. Oh, I forgot a comma for that. Size inputs must be scalar. Okay. Ones. Okay. This is where stuff gets confusing. Okay. Okay. So let's think about this. Okay. So we want 3 zeros right here, right? So instead of doing that, abs n 1. There we go. It's 1. It's 2. Let's run that. What? U zeros 1 abs n. Use parentheses. Come on, man. Abs n of 1. It's probably something really, really dumb. 3. I'm forgetting my MATLAB. Okay, so that's what we want. 1, 1s, 1, 3. This is what we want. So if I were to shorthand this, let's put absolute of n 1. There we go. Get the same thing. Okay. And then let's type in n of end. There we go. I don't know what was going on with me. Figure 24. Copy, paste, boom. Exercise unit. It's okay. U. And delete that. Interpreter. U. Oh, nope. U. There we go. Oh, that took a long time to generate. So now you got the unit step, right? Now we want to shift this. So if I were to do a new time G, let's call it NG, time of G, or no, not G, E. Yes, E, N-E. And we're delaying our signal. So to delay a signal, all delays, if I were to show you a spectrometer, I don't know if you've seen the oscilloscopes, but the oscilloscopes, signals come from the right to the left, so they all like to propagate that way. So if you were to put like a sensor here, all the signals trying to hit this sensor is what I'm trying to say. Here's t is equal to 0. And as time passes, if you were to delay this, it would just shift this way. I don't know how to explain that one, but if you were to see a real oscilloscope, you see all these signals bounce from right to left as they hit this sensor or whatever you're looking at, whatever your cursors are. But that's the real world application. But now for our theoretical applications, if our unit step is this, right? And if you were to delay it, we're going to try and push it to the right, which means instead of this, u of n minus 1 means we're going to have a 0 right there. Point. And that's what it would look like. So instead of it starting here at this axis, it's being delayed. So that means as time continues, as one more point, then this gets right here. So it's delayed by 1. When you have a delay, it pushes everything to the right. And then, well, this is our position. Whatever is delayed will eventually hit this in one more step. I don't know if that made any sense, but I'm trying to get this practical connection between signals and systems, but maybe you guys like math more. But what I'm trying to tell you is to delay the signal, all you do is just -5. That's it. And then copy. Man, all right. We don't have to call, okay, let's call it EU. Okay. So you could have called the same function, or you could just do this, whatever makes you happy. E, N-E, E, which is equal to units of n minus 5. And there you go. That is your delayed signal. Makes sense? Makes easy sense? Are you guys getting this? Is this the best that I can do? Doing your assignment, making sure you guys know what's going on? Because if you don't know how to do this, Then the next assignment's going to start getting harder, and then you're going to start feeling the burn, and oof, it's not going to be fun at the end. But point is, I'm trying to help you guys realize that MATLAB's a really powerful tool. You can do a lot of things with it and get stuff going. Exercise 6. So there's 2 definitions I need to get everyone to learn. And that's a real signal. What's a real signal? And what's an imaginary signal? And then Dr. Stuber starts talking about Hermitian even, and Hermitian odds. That's one of the definitions, I think. So please memorize that. Let's see. Where is that? Definitions. Yep. Where is it? Yeah, Hermitian odd and Hermitian even. Which basically, from what I remember, it's basically a complex even signal, a complex odd signal. So you got some homework to memorize for. So to generate real and imaginary signals, you can do the following. Let's pull this puppy out. Okay. Oh, come on. There we go. For our example, we have e to the j pi n over 5. There we go. Pi n over 5. So one thing I need to ask, what is the magnitude of this? All right, there's only one answer, and please make this a promise. Like, what's the one thing you're going to get out of this class? The magnitude of this exponential, or of any exponential, actually, is equal to 1. Always. It's a circle. It's just a circle, just like that, of radius 1. All right. No matter what your angular frequency or whatever is right here, please don't forget this. Whatever is in here, omega, the magnitude of this will always be 1. So that's your guaranteed. It's crazy how some people will forget that little trick, but it gets the best of DSP engineers. Okay. But now you're trying to figure out, okay, we're trying to get real and complex. So to get the real components, you can just type this into MATLAB. Exp of j, or I, times pi, or pi, times n divided by 5. And there you go. So that's your real, and now you can plot that. Plus m j pi n divided by 5. There you go. So that's how you would do that. Really simple. And I ask everyone to plot the real and imaginary components. So if you were to do the imaginary, you guys can do the real if you wanted to. Exercise 6. So n, actually CLC, C clear vars, n is equal to minus, yeah, remember this, don't forget that, but I'm going to do it from minus 5 to 5. So real E, whatever, is going to be exp j times pi times n divided by 5. And the imaginary, imag E, exp j times pi times n divided by 5. So this basically gives us, oh wait, I didn't even type that. Real, the function real just gets the real values of this. And then m think that's the word. I think it's in. Help him. Oh, it's a mag. So I should probably write that down. Okay. Here we go. A mag. And figure. There we go. Stem. Let's plot just the real part, or imaginary. E. Title. Of e to the j frac pi n 5. Let's put this money sign interpreter, text. Oh. And there you go. And Y label, val, pretty graph. Whew, there you go, and that's your imaginary values. And as you can see, and if this doesn't make any sense, let me show you. If e to the j pi 0 over 5, what's this going to equal to? It's going to equal e to the j 0, which means you're going to get a real part plus j 0 imaginary part, which means for our imaginary plot, we should get a 0 at n is equal to 0. And is that what we get? Yes, right here at 0, we get 0. Which means the real value should be right there, so, or in quadrature is the word. In phase and quadrature. This right here is our quadrature signal. You get to see the in phase one later on. So I think that covers a lot of material for today. Hopefully this was helpful. I want to make sure everyone knows that this assignment is here to get you started with MATLAB. Like everything I'm doing right now is like the bare minimum. If there are any tricks that you know, like, oh, making prettier graphs, you could use subplot, but it's too early for that one. Don't worry so hard. But everything I'm showing you right now is everything you ever need for this first assignment. So this should be a good help for everyone. Try to get this done as soon as you can. So hopefully by Friday, maybe I can try to help you guys study for the exam. Because I know you guys don't have a study session. It should be this Wednesday, but it's okay. Don't worry. Point is, I want to make sure everyone knows what's going on. So with that, I think that's about it. Let's see. Maybe I can play a quick demonstration if you want. All right, y'all. Take care.